having something that can fly at 400 knots and do vertical takeoff and landing is something that frankly doesn't exist right now, or if it exists is the F-35 or Harrier type of aircraft. But this would be something smaller, and think about the possibilities and the payback for that is just tremendous, right? I mean, think about the golden hour. Think about how you can scale up and you can save lives because you move 3 times faster than a helicopter.
Hey everyone, and thanks for listening to another episode of DIB Innovators. Today I'm speaking with Andrei Evulet, co-founder, CEO, and CTO of Jetoptera. Andrei, thanks for chatting with me today.
Hello, Dave. Thanks for the intro and the opportunity to contribute to your podcast. I'm very happy to be here.
Yeah, no, this is exciting. I think you've got some really cool tech, to peel back and just breaking down some of the walls that have existed forever in aviation. So before we get there, though, talk to me about how you came to the point where you founded Jetoptera.
Sure. My journey in aerospace started in Romania, where I was born. I grew up and completed my engineering degree in aerospace engineering. Then I worked for a institute where my job was to turn MiG-19 engines into aeroderivatives and turbo generators. I have a Bachelor of Engineering from Aeronautical Engineering in Manchester, UK. Then I earned a PhD in Mechanical and Aerospace Engineering at Rutgers. Started almost immediately to work for General Electric's Global Research Center in Niskayuna, New York, where my job was to develop novel gas turbines from microturbines to aeroderivatives and aircraft engines for propulsion. Use of hydrogen in gas turbines. I burned a lot of hydrogen in the tests, and more advanced things like exhaust gas recirculation in gas turbines, which was a novel thing. Spent then 2 years at GE Oil and Gas in Florence, Italy, leading the combustion group there. That was developing a new aeroderivative for mechanical drives and turbo compressors for the oil and gas industry. But my last 4 years with General Electric were in Cincinnati, Ohio, working as a systems engineer and later becoming the technology maturation and integration leader for the GE9X, which is the most powerful turbofan ever produced that powers the Boeing 777X. And that was my pinnacle of my GE career, where I learned a great deal about several industries, about research and development, I had contributions to several products in propulsion and power generation. When the design of G9X was completed and the configuration frozen, I decided to co-found Jetoptera after I recognized the incredible potential of using drones in both military and commercial applications. I also realized immediately that the potential of innovation in that space, especially the vertical takeoff and landing or VTOL capabilities, and the need for a novel propulsion system that is better than the electric VTOL toys that, frankly, Jeff Bezos was talking about. And that year was 2015.
All right. So then you founded Jetoptera to do that. What does Jetoptera mean? Is there a meaning behind the name?
Yeah, absolutely. It's a combination of the words jet and ptera. Ptera in Old Greek means wing. And if you get into the details of our technology, you'll see that we're using a special type of ejectors that we can give non-round shapes and make it conforming with the wing. So by doing this, you generate more lift using the jet flying on top of the wing. It's a combination that NASA also tested way 30 years ago, 40 years ago, called upper surface blowing wing. But we've perfected this type of approach. So the name Jetoptera is perfect for what we're trying to do.
That's great. And so what is behind the technology in this? I know how a turbine engine works. I think many of our listeners know that. What is the difference, and why is there an advantage or a use case that you see to be a good market fit?
Yeah, sure. Well, at the core of our system is a turbo compressor. And this turbo compressor is taking ambient air and compressing it to a certain pressure ratio and flows that we need to push through a pneumatic system to our ejectors. The system is an ejector system that admits this compressed air. And by the way, the turbo compressor could be any turboshaft engine from less than 100 horsepower to over 5,000 horsepower that we can turn into an axial compressor. We need that core air, the compressed air, to actually feed this thrusters, this invention that I made, which is a special type of ejector that amplifies the air. So basically, what an ejector does is, if you think about that trickle of air that is produced by the compressor, it's in fact a turbofan, if you will. We augment the force that is created by that compressed air operating as a turbofan 2 to 3 times. So basically, especially at static conditions, namely a vertical takeoff and landing application, we augment the thrust, and with the same system, we produce 2 times more thrust than otherwise entitled to produce. So that's the principle. Of course, the ejectors could be given non-round shapes, and that's a huge advantage because now you can think out of the box and think about combinations between the airframe and the propulsion system that don't exist with legacy systems. All legacy systems have something that is round and spinning. Ours eliminate any moving parts on the outside of the aircraft. The turbo compressor would live inside the airframe. So therefore, what's outside, it has no moving parts, produces a stream of air that has no tones because the propeller chops the air at a certain frequency. We don't have that. And that's immediately a benefit of 20 to 30 decibels lower noise because we have no tones. We're atonal. The other thing is that we can make these things, the ejectors, we call them thrust augmenters or thrusters augmenters. So give them a configuration or a shape that can actually be retracted into the wing. And that's extremely important because for a vertical takeoff and landing application, for instance, you can deploy these thrusters, take off vertically, and then when you move faster, you can retract them into the wing, and then now your turbo compressor can operate as a turbofan. So now you can think of Mach 0.6, Mach 0.8 capabilities with this airframe that can also do VTOL. It's a game changer. The last considerable benefit that we have is the fact that by entraining massive amounts of air with these thrusters, we, by the way, 20 to 25 parts of air entrained, we have a very low infrared signature. So we can actually, become very LPD, low propensity of detection, and high survivability elements are part of the solution.
Interesting. So if I were to just think of normal aeronautic flow with like turbojet engines or engines, we're compressing air, we're then igniting it, with fuel, and then we get an increase in thrust out the back. How are so you compress the air, what are you doing to then increase that flow? Is there still ignition that's happening there, or what is?
No, it's more, a better comparison is if you think about, let's say, a military turbofan. You are familiar, of course, with the bypass air. So there's a bypass air from the turbofan that typically is being pushed in the back and in a concentrical manner, right, to the core, which is doing the combustion, as you mentioned, right? But the bypass air is not being burnt with anything unless you use a post-combustion augmenter. But in our case, what we do is we collect that air and we run it through a conduit system to distribute that thrust, if you will, and the thrusters across the airframe. So no longer your bypass air is being supplied and being dumped in the back, concentrical to the core jet, but we're using that air to generate twice the thrust with these devices that we place in strategic places, if you will, on the airframe. And that's the principle. Now, the best part of it is that you could then bypass this system, this pneumatic system with conduits by shutting off some valves, and then you force the turbofan to operate as original intended. So you retract the ejectors, and then your turbofan operates as intended as a turbofan for the high speed. So the mission would look like thrusters are out, you work with flaps, you blow over the flaps using these ejectors. The turbofan feeds these ejectors across the airframe. Up in the air, you transition to forward flight, and at some point in time, you retract your flaps, you retract your ejectors, and now your turbofan is doing the propulsion moving forward. But you also have achieved a more streamlined airframe, allowing you to go at faster speeds. And we have verified, we have data to show that we can do this from one of the sitter programs that we did with the DoD, in which we tested the subscale model in a wind tunnel with and without the thrusters.
Interesting. So you have an engine, so you still have to bring in air. So where doesn't matter now where you put the intakes, right? You can put them anywhere to bring in the air. How do you envision that most effectively with the compressor?
Yeah, it wouldn't be different from the current arrangement of a turbofan on a military aircraft. The difference is that we do bury the, if you will, the engine into the fuselage. So that benefits us from a number of reasons, especially on the military applications. A lot of noise can be actually abated from the turbo machinery itself. And then the conduits are also part of so that's the part that's going to take some space from inside the airframe. These are conduits that run 100 to 150 degrees Fahrenheit pressure 2-to-1 air to the thrusters. But yeah, otherwise the intake would be very similar to what you have today on turbofans.
Very interesting. So talk to me about, are there use cases where, so obviously the takeoff takes, a couple times more thrust than it does to go forward. And so you're able to achieve that thrust with this. What's your best, forward velocity with this type of setup? And obviously it probably depends on the size of the engine, but all those pieces, but are you able to establish a decent forward? If you didn't retract them, you just left them out and let's go.
Right. So if you were to use the thrusters augmenters on the wing, you could go as fast as, let's say, 200 knots. But beyond that speed, that forward speed, you would have to, whatever you gain from a thrust augmentation, you lose by inducing more drag. So therefore, beyond the 200 knots, you would have to retract the thrusters or hide them, if you will, into the fuselage and rely only on the engine. But that does two things. Number one is the turbofan operates normally as a turbofan, but the airframe becomes very streamlined. Now, remember, the V-22 has a very serious forward speed limitation because of the large rotors, right? But in our case, we have data from the wind tunnel where we can push Mach 0.6, Mach 0.8 in forward speed once we have retracted this thruster. So we tested a wind tunnel model where we did both thruster on the wing and thrusted retracted, and we confirmed that theory.
Well, really, the forward thrust, correct if I'm wrong, it would just be the amount of thrust for the forward speed, the amount of thrust you could, you're a cleaner airplane because you don't have,
exactly,
it's more aligned with the current, aircraft.
Yeah, and if you put the nice thing about our technology is that you're also relying on a ubiquitous gas turbine, right? If you look at the helicopter world, 90+% of the helicopters use a gas turbine. But we use this gas turbine that we turned from, by the way, you can turn any helicopter engine into a compressor because all you have to do is, it's a turbo shaft, really, that you, instead of driving, through a reduction gear, a rotor, you would replace that with the axial turbofan, right? So any engine, any turboshaft that exists less than 100 horsepower to more than 5,000 horsepower, you can scale up our technology as well. And it would not take a large effort to actually turn this existing engine into or a turboprop engine, like the PT6, for instance, or a helicopter engine like the T700 into a turbo compressor. So the neat thing about this is that the gas turbine is very powerful technology in terms of power to weight, right? Much better than anything else out there. And we add some weight with the pneumatic system and the ejectors. But the great thing about it is that we can 3D print, we can manufacture this ejectors via additive manufacturing, and we can make them thin enough so they keep the weight relatively low. So we have recently demonstrated a 250-pound force system with such an ejector, which we tested with the help of our friends from Aerotech, one of our subcontractors. And we have a very good path forward to scale it up to thousands of pound force as well, while keeping them very light.
Yeah. So why are you limited to 5,000 horsepower?
Yeah, that's the largest. I think the largest turbo prop that exists today. It's about 5,000 horsepower. That's a very large application. Although I think there's a Russian, I think it's a Russian or a European, in any case, European application that uses even larger turbo shaft engines. But now we're talking very large systems. Our plan is to start with unmanned, de-risk the system, start growing and growing with larger and larger systems until we get to 20,000, 30,000 pound MTOL. So basically, aircraft that can compete with helicopters. It's very important to mention that although we could, in theory, switch to an all-electric system, the battery is nowhere near the performance that we need for vertical takeoff. So we have dismissed from the start the idea of going eVTOL, electric VTOL, because the battery is not there. However, if a battery is invented that can actually be competitive with the jet fuel in energy density, we can switch to that as well. And we have tested with electric compressors as well. But right now, especially for military applications, there's nothing better than the jet fuel, and we stay with the jet fuel, and the compatibility with the gas turbine is 100%. So
how have we looked at hydrogen? Just out of curiosity.
We looked at hydrogen, and by the way, hydrogen is kind of a straightforward. A gas turbine can take a lot of fuels, right, including hydrogen. If you think about the history of gas turbine, the invention of the gas turbine, when von Ohain first tested the very first propulsion system with a gas turbine, he used hydrogen. However, it's not a practical fuel. We know we can burn it. We know we can use it, but storage on board of the aircraft is a completely different issue, plus the manufacturing of the hydrogen. So until a hydrogen economy develops and a way to store that hydrogen, probably storing it in a nano powders that can store hydrogen different than liquid hydrogen, which is a nightmare to store on board of an aircraft, then we'll stay put, and we're going to use jet fuel or diesel. We could use diesel as well. Jet fuel and diesel are not that different to each other.
Doesn't matter. You just need something to power the compressor.
Exactly.
Yeah, that's fascinating. So why did you start focusing on this? Like, what was the idea behind, like, this is going to be the next thing?
Yeah, so I spoke a little bit about 2015 when kind of like the light bulb lit. Two events actually contributed to that. So I was still working for G at the time. In 2014, Jeff Bezos came on 60 Minutes and started talking about commercial application of drones for delivery. And I looked at the time at the eVTOL and this multi copters, and I was thinking, well, that may be good for up to 5 pounds payload, but you can't go too far with that, and you're gonna need something much bigger. The second event that happened, that was in April of 2015, if I'm not mistaken, was the Kathmandu earthquake. And it was unbelievable to watch this crisis that was happening. Infrastructure was completely destroyed, and these people in the villages could not get any help for weeks because they only had maybe less than 15 helicopters available. One was lost, by the way, with all 6 souls lost on board. And I thought, wow, this is something that needs to be addressed. I mean, more recently, Helen, the hurricane, showed the need for such a system that people look no longer to the roads to get help. They look at the sky, right? So especially when you're isolated and time is of essence, right? You save lives. You need something that is a vertical takeoff and landing system that can be runway independent, that can access even places where a helicopter might not be able to land. Like, for instance, due to the large rotors, you cannot land in a forest or somewhere where you have all kind of wires, etc. And something that moves much faster. So these things, to me, they look like, hey, let's take another look at ejectors. And I did the fair share of reading literally hundreds of papers that were written in the past about ejectors. A gas turbine powering ejectors sounded to me like the right approach there. And we have several very, very compelling advantages to rotary wings and systems that use multicopters. One is the noise. As I mentioned, we're atonal. And as part of a contract with the DoD, we have hired a specialist in acoustics that measured this noise from our system and compared it to an equivalent propeller. And he was the one who actually mentioned that our system is atonal, no tones, no frequencies, and that it's and I'm quoting him, it sounds more like the wind as designed. That guy is a specialist who got eventually an aeroacoustics prize from the AIW in I think in 2021. And then the other benefit is obviously we have no moving parts. That's going to be a huge advantage in terms of safety, right? No rotor hitting a wire or a tree or bushes or whatever. It opens up the space where you can land and where you can take off from. Unprepared surfaces, runway independent. And maybe the most compelling of all is the ability to go to very high speeds. This is something that, obviously the V-22 is the workhorse today in terms of deploying troops with a higher speed to a location. And it has many advantages over helicopters, right? But it's still about one half of the speeds that we can do, maybe even 1/3. And this is something that we actually confirmed under a program, also a DoD program called High Speed VTOL Challenge, in which we partnered with Pratt & Whitney, who validated our idea of using a turbo prop to turn into a turbo compressor, and with Northrop Grumman, who validated our capabilities in terms of designing an airframe that can do this kind of speeds. So these are the 3 main advantages that we bring to the table with our system.
I mean, it's similar, I guess, a little bit the FLRAA program, so the Future Long Range Assault Aircraft for the Army. I mean, it seems like you're intersecting with that, but your tech may be a little, latent for that, program. Do you think that's also part of that fit?
Yeah, absolutely. In fact, we another program. Unfortunately, we didn't get funded, but another program was the DARPA Sprint program. And to be honest, we were very frustrated not to get the award because, in my opinion, we had one of the best solutions out there to achieve this high-speed VTOL concept and make it work. But the Army program is also on our radar. It started already, so it's a little late.
Right.
We're gonna try to do this with small unmanned first and show how we can scale up the technology. And right now, to that end, we have a commercial program with an entity, a company in Dubai who's interested in unmanned drone commercial drone delivery, but also right after that, they want to implement a air taxi that uses our system. So we're getting into the manned application. So, but we're going to take it one step at a time. Unmanned first, which is a 500-pound MTOW aircraft that can carry up to 100 pounds of payload, and that can go as far as 200 nautical miles.
That's super exciting.
That's going to fly. That's going to fly next year at some
Yeah, I
point.
was going to ask you, where are you in your development and proof of concept?
Yeah, so right now we're manufacturing the turbo compressor for this application, which is based on a 250 kilowatt. It's going to be a 250 kilowatt based system, turbo compressor. Then we have already manufactured multiple parts of the. So we passed the critical design review, and we're now manufacturing the thrusters. We demonstrate the 250-pound force capable thrusters and the front thrusters on this platform. And we started the manufacturing also of the airframe. So it's an ongoing process that's going to take another 6 months or so until we actually integrate the aircraft, and then we're going to start the campaign.
So that is interesting. I guess when you take and you have this compressed air, how many thrusters can you send it to? And is there an advantage to that, or is one thruster? It just depends on how many.
That's a great question.
Ejectors you have.
That's a great question, and it depends on the mission and the platform you want to develop. So basically, when we demonstrate our first concepts, which is basically an oval type of thrusters, you can see on our website the flight test bed that we're using to test.
Is that on the picture behind you? Is that on that blue picture behind you?
No, that's going to be the future concept.
Okay.
That's going to be what we're going to build. That's the J2000 we're going to build with this Dubai company called Inan for their application in Dubai. And that's a two-seater. So that's a 2,000-pound MTOW. No, but what we're using a 7-meter wingspan glider, which is powered by our system alone, and we test various configurations on the system. But back to your question, it depends on the application you want. If you want something that can do, let's say, a cargo delivery, whether commercial or military, and you can use this kind of configuration, a box wing and canard that we came up with and patented. By the way, I forgot to mention we have 150 patents on this technology, the propulsion technology. Internationally, so you can deploy this type of configuration. And the idea behind this configuration is that you're more compact, you access more places because you're silent. You can operate 24/7, and you're not restricted by that. But you land where helicopters cannot land, or even multicopters, because of the constraints of the landing place, landing zone, right? Or you can deploy the very same core system, but with multiple thrusters in a different configuration, such as a high-speed VTOL. And that's going to look different. It's not going to look like the box wing, because you want to go faster than 200 knots. It's going to look more like a normal or blended wing body aircraft. There are so many combinations you can think of. We can even think of retrofitting existing systems. I mean, we've looked at retrofitting, for instance, Rutan's aircraft, or a simple Cessna. Just going from a propeller to our system would actually be maybe not as efficient in terms of fuel burn, because the turbine is more thirsty than a Continental ICE. However, that Continental, the internal combustion engine is very heavy, whereas we are very light. So these are the trade-offs, if you will.
Yeah, because I look at that picture behind you. I mean, I guess you're also doing the airframe design behind your platforms, or are you licensing this? Are you considering licensing? Because I imagine, a VTOL, where your thrust's going down versus where the weight distribution is of the platform creates some issues, and how you manage that.
Yeah, yes, we have the patents for both the airframe and for the propulsion, but the main thing is the propulsion system. We have all these patents, right? We have been very successful to keep the team very small, but work with very trustworthy. We build a network of subcontractors that we trust very much. So, for instance, in the propulsion, the turbo compressor manufacturing world, we have been very successfully working with a company called Parametric Solutions from Florida, in Florida, and in the airframe and the rest of the design. We've been collaborating with Aerotech here in Washington State. So the idea is to, yes, we're open to licensing the system as well. And yeah, the idea would be for certification down the road, we would still partner with somebody who has a dedicated team to certify. Now, keep in mind for the propulsion system, like I said, you start from a certified engine like a turboprop, and the delta to spend on certification is going to be far smaller than if you start from scratch, like all these electric VTOL companies are trying to do today.
Interesting. Do you have any competitors that are looking at this, or do you own this kind of concept from, soup to nuts?
Well, I mean, I'm very proud of what we achieved in terms of IP, right? I mean, it's very hard to obtain patents in this world, but I'm happy to say that we're one of the very few, you can count them by hand, that we know of, ejector type companies, and we feel like we're going to be very a very strong presence in that area. Competitors, I mean, you see a lot of hype, I'd say, with this electric VTOL. I don't think it's going to last much longer because the assumption of the battery evolving, as fast as the Moore's law in chips, technology is not real. And I have a lot of experience that even at GE, one of the benefits of working at the GE Research Center was that you interacted with battery scientists, with fuel cell scientists, MRI scientists. It was a great hub to learn new things, and you would see the problems right there. So people with experience in batteries realize that, hey, it's a huge challenge. And even the eVTOLs, the question is the market really for an VTOL aircraft that can only do 20 miles when you carry the payload? Or is it really a market that, or do you really want to address the market of the helicopters, which is very clearly understood? It's, 150, more than $150 billion a year of a market. So we start with unmanned, but our challenge is basically our goal is to challenge the helicopter. And we're going to challenge it by offering something that is more silent, relying still on a gas turbine and jet fuel, but ability to move faster than a helicopter, and like I said, accessing far more areas than a helicopter can do. And that's of great interest also in the military, in DoD as well.
Yeah, so you have done a lot of, it appears just through research, you have a fair amount of military kind of grants and awards and, opportunities. Can you share our insights on some of this collaboration and maybe, how
Sure.
they've influenced your roadmap in your development?
Yeah, absolutely. I mean, it's great when you get, non-dilutive funding, right? You learn quite a bit about your own system. So this is how we learned, for instance, on one of these subcontracts, actually, to another company. We tested our FPS, and we learned about the atonality, the lack of frequencies, and the huge benefits in noise, right? That was a program for a company called Freedom Flight Works in California that's developing for the Army, US Army, is developing what we call now a fluidic propulsion system powered parafoils. So basically, the idea is that you can make a drop instead of dropping it right on top of the landing zone or a target. You would drop it from far away, and you will propel the resupplies with a parafoil but you have to be silent, or you have to be go undetected. That's one project. So parafoils, that's like a smaller system for now, but we're looking at larger systems as well. And that's the Army. With the U.S. Air Force, we had several programs. In total, we had 11 contracts with the DoD to date. Some of them were subcontracts to like this parafoil propulsion, but some of them we were principals. We had both SIBRs and sitters, phase ones and phase twos. We didn't get yet a phase three, but this allowed us to do so many things. I mentioned earlier the upper surface blown wing. Well, we were able to go under a sitter phase one and later under a sitter phase two with a full model of an aircraft and test that theory, right? And we got excellent data and validation of the concept. We had the high-speed VTOL challenge, AFWERX sponsored that, where we, like I said, we were one of the 5 companies that actually were selected from 250 plus companies that applied. And we partnered on that program with Northrop Grumman and with Pratt and Whitney. Again, validation. So this is the path that we went on, and we validated all that we've done with experimental or with partnerships. So we're excited about this commercial one because, again, this is a non-dilutive deal that allows us to put out there on the market the first ever VTOL cargo aircraft in Dubai. And that's the path we're on. Right now, the best development for us would have been to win that DARPA Sprint program, which was 4 years program to develop a high-speed VTOL concept and demonstrate an X-plane, pretty much. But we didn't get it. So now we're trying to compensate in some other way to demonstrate that capability in flight.
So do you still see a demand signal that is leaning towards eVTOL? Is that just because batteries are more proliferated than this other type of technology? Or do you see that that's not even really bearing?
No, I don't.
Because of the weight of the battery.
It's a number of things. It's not only the battery. The battery is for the, let's put it this way, for the technical reason, I don't think the battery will ever be able sufficient and safe. Very important, sufficient and safe. Okay, thermal runaway is still a problem. Last time I checked, Teslas or other cars can burn, and accidents can happen. But I think also from the economics viewpoint, it is very improbable that a huge market like was mentioned, trillions and trillions of dollars, are going to be of eVTOLs that fly over a city and cover 20 miles. So I really don't think, and you already see signs of fatigue, if you will. 2 companies already declared, or one declared bankruptcy, Lilium in Germany. Another one is close to bankruptcy. So I think the battery, the market, and really the certification, these 3 elements will actually, put an end to this bubble, because that's what it is. We never went all electric for that reason. We wanted to stay developed with the gas turbine based technology, and actually we were vindicated with that. If you look at the big players, Honda announced recently that their eVTOL is actually a hybrid system that is based on a turbine that is a turbo generator. So they didn't even try to go to batteries. And I don't think the battery based systems are ready, or will be ready, frankly speaking, 20, 30 years from now.
Well, especially for the size you're doing. I mean, to your point, a small quadcopter that needs to go 5 miles to drop off a toothbrush to someone's house, that might be a good
Exactly.
good use case. But
yeah. Well, I'd add this thing. Think about, definitely it's a business that needs a lot of capital. If you look at Amazon, they spent $1 billion until 3 years ago, I think, and they almost declared the program dead. Right now, they spend the second $1 billion, and they have something. I think they're doing demonstrations in Arizona. That's an all-electric system, And even today they report fires in the field and all these issues. I really think that there's a market. The market you want to go after for the manned is really helicopter market, because it's an established, mature. We understand how it works and all that. And the second one is in the area of unmanned. You got to be able to do things that electric VTOL multicopters cannot do, and that's going to be us.
Absolutely. So let's go through a couple of challenges you see from a technology standpoint. What are your biggest challenges or hurdles to overcome?
I'll tell you what the challenge is. The challenge is capital, capital, capital. We're burning so much capital that it's limited in what we can do. We had technical challenges. We had incredible difficulties finding turbo compressor manufacturer for the past 7 years. If you look at what's going on in the world right now, there are very few manufacturers that actually can produce, let's say, a 100 to 200 kilowatt turbo compressor. Because every time we approached one of the OEMs and we told them what we want to do, they said, sure, it's doable, but where's the money? And the money is usually when you talk to the large OEMs is in millions and millions and millions, which we didn't have. We have struggled with that quite a bit, and sometimes we even went into endeavors where basically we had to give up and change the players. So it wasn't trivial. But other than that, we use additive manufacturing has been a tremendous, tremendous enabler for us. My theory is that in the past, when NASA tried ejectors, and I spoke with somebody who was in the field back then at NASA, and he told me, look, back then it was a very artisanal kind of an approach. You had two technicians who knew how to bend metal, to change things, but it was very, very erratic in terms of they changed something and they would see that the performance goes away, or vice versa. And they didn't do a very very thorough investigation. We took a different approach. I used all my experience that I gained over the years, and at G9X, when I was technology maturation and integration leader for the G9X, I was basically in charge of 70 different rigs and technologies, from the 6th generation composite fan blade to all the way to 11 stage 27-to-1 compressor, pressure ratio compressor, to ceramic combustors, to 3D printed LPT, low pressure turbine. And I learned quite a bit what's doable and what's not doable, of course, at different scale. But our approach on Jetoptera was basically, we started literally with looking at using additive manufacturing, 3D printing, to 3D print very many designs, options of these ejectors, and we tested them all. Funny story, the way I tested this was I was still in Ohio after working for GE, and I was testing, I rented a tow behind diesel compressor, and I was testing in my driveway and in my garage. And luckily for me, all my neighbors were ex-GE aviation guys who came out to help, not to complain. But we built a rig, we 3D printed hundreds of these designs, we tested them. I built a little scale to load cell to measure the thrust and the performance. And that's how we started. And we down selected a couple of them. And that's how we went about to do it. But yeah, the turbo machinery was a challenge to find the right partner. We did find it now. And I think the other challenge was obviously raising money. That's one of the challenges that I had, was literally when we go to all these VCs, everybody wants to be the Tesla of the skies. And I explained to them, look, our system is agnostic, okay? But let me start with jet fuel and I can migrate. I'm not a battery company. I'm not developing batteries. That's a tough thing. I'm not that smart. But when a battery is invented, you can actually switch overnight. Literally overnight, you can switch to an all-electric system, but you need that battery. And right now they're at 300, 350 maybe watt hour per kilogram. And, when you compare to the jet fuel, energy density is like a factor of 40, 50. And that's not something that gap is not going to be built, in the next 2, 3, 5 decades. I think the gas turbine is going to be here to stay. It's going to be a major player even in unmanned, or both military and civilian applications. So we're going to stick with the gas turbine and with the jet fuel for the foreseeable future.
Right. So from a capital perspective, how much have you raised, if you can share? Like, have you raised?
I can give you a rough, all these numbers I give you are also public because we did a couple of crowdfunded sessions, right? CF, Reg D. We raised money, friends and family at first. Altogether to date, I think we raised around $13 million over the past 9 years. And plus the non-dilutive part, which I'd rather not talk about from the military, but that's the level we've raised to date.
That's great. And you're going to continue on that, obviously to raise more and continue to progress this.
Yeah, on the civilian side, we're going full speed with this, with our customer from Dubai. On the military one, obviously, we want to expand, go to larger and larger systems.
Well, it's a super exciting time. You've got some very cool things that you've outlined. I really do appreciate you sharing.
Sure.
How long do you think till you have a fully operational, contracted or purchased, vehicle using this technology that is for sale or, operating in the military?
By mid of next year, 2025, we're going to fly the prototype, or maybe third quarter. You know how it is with these programs. We're going to operate this J500, we call it. 500 stands for 500-pound MTOL. We're going to operate that in Dubai. So that will be the prototype. That will be also a product offered. It would be offered here in the States as well. So it's not exclusive for the UAE market. So that will be already a prototype and already offered as a product. The next step with Inan from Dubai will be to move to the air taxi. And that's going to take, a few years to build a prototype, followed by another year or so of certification, etc. But in the meantime, obviously, we have other ideas, and we're open to anything that the DoD would like to do with our system as well. I think I would be very excited if I can get the program to demonstrate our HS VTOL, because that's a game changer. Having something that can fly at 400 knots and do vertical takeoff and landing is something that, frankly, doesn't exist right now. Or if it exists, is the F-35 or, Harrier type of aircraft. But this would be something smaller. And think about the possibilities and the payback for that. It's just tremendous, right? I mean, think about the golden hour. Think about how you can scale up and you can save lives because you move, 3 times faster than a helicopter. You can access places where a helicopter can't go, and so on. So these are the directions we're thinking right now, and we're trying to find the right platform to do it.
Yeah, that's super exciting. Well, I really do appreciate it. Unfortunately, we got to wrap this up, but this has been super fascinating. I wish you the best. I think what a great idea and opportunity. So anything, if people want to follow what you're doing or get involved or, learn more,
sure,
how would they do that?
Yeah, on social, you can follow us on at Jetoptera, or you can follow my profile as well. We're also on X, Twitter, at Jetoptera as well. And visit our website. Our website, I have to say, we haven't put a lot of money in development. We have just a couple of animations, but a lot of video from the past, so you can watch that R&D video. And we try to keep up with it, but that's not the focus. The focus is raise capital and build more platforms. So that's in a nutshell where you can follow us. We're also on Facebook, actually.
Oh, there you go. Well, that's great, Andrei. Thank you very much. And let's stay in touch. I can't wait to talk. Let's connect again when you get something going a little bit further, and love to just hear the progress.
My pleasure, Dave. Very nice to meet you, and hope your audience is going to enjoy this.
I think they will. Thank you, sir.